Hello, this is Shengying Zhao at Harbin Institute of Technology. In our group, ongoing research is on the mechanical behavior of cement-based material that incorporates an additive called superabsorbent polymer. The research is based largely on modeling work. I'm going to start with introducing how this additive works in cement paste, and then talk about how we model the mechanical properties and where the inputs come from. After that, I'll show some results and discuss them. The powder-like additive is superabsorbent polymer, or SAP in short. If you mix it with cement and water, it will absorb some water and expand. If you don't want SAP to reduce the water to cement ratio, you'd better add some extra water. As cement hydration goes on and internal humidity goes down, the SAP particle gradually gives off the water it has taken, shrinks, and leaves a cavity in the cement paste matrix. And that's the basic idea of internal curing. The amount of extra water should be carefully controlled. Otherwise, you end up with too much water in SAP, in concrete. It is not fair to draw a conclusion like SAP reduces concrete strength based on an erroneous absorption capacity. There are many ways of measuring the absorption capacity of a SAP, and we investigated some artifacts of the measurement and how we can improve it. Both papers were produced at Technical University of Denmark through in-depth discussion with Ole Jensen and Marianne Hasselt. I'm indebted to them. When we have carefully controlled the amount of extra water, does SAP concrete have a strength or Young's modulus as good as a concrete without SAP? Well, there are at least two other factors. First, the SAP voids have a negative effect. The larger the void content, the worse the mechanical properties. On the other hand, the cement paste surrounding cement particles have a higher degree of hydration and a lower capillary porosity, probably because of the internal curing effect offered by the SAP. This part of cement paste is called internal curing zone. So our aim is to build a model where we take into account both the negative effect of SAP voids and the positive effect of internal curing. Specifically, we want to look at the tensile strength and Young's modulus of a cubic cement paste with SAP and compare them to those properties of cement paste with the same content and distribution of air voids, but with no internal curing zone, and of cement paste with neither air voids nor internal curing zone. The cubic we are interested in has a net length of 40 millimeters, far larger than the dimension of SAP voids. So we use the so-called multi-scale modeling approach. That is, we kind of break the cube into smaller cubes. When we have got the strength and modulus of the small cubes, we integrate them into the larger one. Unlike the conventional finite element method, we use a discrete element method called the lattice fracture analysis, where a continuum, like a concrete, is discretized into interconnected beams that form a lattice network. The behavior of the continuum is represented by the response of the lattice network under load. For example, a crack in a concrete is formed whenever a beam in the network cracks. For the smaller cubes, you have to generate non-overlapping voids. And then you know what phase each of these nodes represents: void, cement matrix, or internal curing zone. Each of these constituents has its distinctive Young's modulus and strength. Then we get the modulus and strength of each lattice beam from the two equations shown on the right that are generally used for lattice fracture modeling. Obviously, the strength and Young's modulus for voids are both zero. For cement paste matrix, the two properties are obtained from validated results in the literature. For internal curing zone, it is found by micro-indentation that the farther the indentation point is from the sap particle, the lower the micro-hardness. As the sap particle used in cement paste are often in a range of diameter, it is reasonable to assume that the Young's modulus at a point depends on the relative distance x, which is the distance of the point to the center of the sap particle relative to the sap diameter. The data points are fitted with a quadratic function that we use to describe the relation between the Young's modulus increase and the relative distance. We temporarily do not consider the superposition effect of internal curing. We just talk about the Young's modulus. What about the strength? Well, the relation between strength and capillary porosity has been well established. So has the relation between Young's modulus and capillary porosity. Based on these relations, we correlate strength and Young's modulus and find the curve is very close to the line of equality. When the Young's modulus of every node in the lattice network is known, you have the stiffness matrix K built. With a boundary condition applied, we work out the displacement vector U. Then you figure out the internal force of each lattice beam, and finally stress. When the stress of the beam exceeds its strength, which we just talked about, it is considered broken and removed from the network. Then you modify the matrix and then apply load again and repeat the computation until the whole network fails. At each load step, you register the load and the elongation of the cube. Here's a picture of 3 types of models we built. The color gradient indicates the Young's modulus of the lattice beams. There's one comment. You don't see too many sap voids in the model with AEA. This is because the lattice beams are so densely arranged that the voids are covered and invisible. For the smaller cubes, their response under uniaxial tensile load is shown in the graph. As expected, the cement paste with no AEA or sap has the highest tensile strength, followed by the cement paste with sap. However, the Young's modulus of the two pastes are very close. The paste with traditional AEA shows the lowest strength among the 3, as well as the lowest Young's modulus. The stress-strain curves are going to be used as input for the larger model, but as they contain too much information, the curves are simplified into multiple segments. That means for the larger model, a lattice beam will have a strength of P2 at the beginning, and when its stress reaches P2, its strength will become P3, etc. When these paste models at a larger scale are subject to compressive load, we can see that the strength of sap-containing paste is 30% lower compared to the cement paste with neither sap nor AEA. But this value is still 75% higher than the cement paste with AEA. On the other hand, the Young's modulus of the sap cement paste is slightly lower than that of ordinary cement paste, and this modulus is 40% higher than that of cement paste with AEA. In a way, our model can explain some observations that were once difficult to explain. For example, some researchers investigated the compressive strength of cement paste with different sap void contents, both by means of experiment and by numerical simulation. At a certain void content, the measured strength is much higher than the model's strength. Why is that? Well, this model took only the sap voids into account. The model didn't assign the internal curing zone higher strength or higher modulus values than the cement paste matrix. So actually the model curve seems to be a curve for AEA cement paste, not for cement paste with sap. Therefore, we believe that our model is a slight improvement in the sense of considering internal curing zone. Here we want to stress that the results I just showed are preliminary results. The results may vary a lot depending on parameters like void content, thickness of internal curing zone, and the extent to which the modulus increase caused by internal curing. For example, when the sap dosage is as large as 5% relative to cement mass, the strength of paste may decrease to almost nothing. At a certain mixed proportion, the compressive strength of sap cement paste can be equal to or even slightly higher than the cement paste without sap. Therefore, a sensitivity analysis is underway. In this sense, we cannot make any conclusions at the moment, but I'd like to summarize today's talk. Our model based on lattice beam network has the merit of considering internal curing zone. This is done by assigning beams increased modulus and strength, the data of which are based on other researchers' work. At a fixed sap void content, internal curing effect, etc., it seems that the cement paste with sap has a much larger compressive strength than AEA cement paste does, but still lower than the strength of ordinary paste. In addition, sap cement paste is very close to ordinary cement paste with respect to Young's modulus. However, the extent of internal curing effect is not fully understood. Further work will focus on getting more reliable data on the microstructure of internal curing zone, and when this is done, the model will be updated. Also, the mechanical property may not only be influenced by internal curing and sap voids, it may be also influenced by the water released by sap, and this might be an area of interest. I'd like to thank Hongzhi Zhang, who used to work at TU Delft, and now I have to close, but I'd like to take some questions from you.